Alright, section 2-8. Something to keep in mind here is if you see something like this, bunch of dots here off to the side, or something here that says type here, don't write that down. That's not going to be in the final draft of the notes. It's not the way the notes are going to look at the end of the day, so don't write that down verbatim. But 2-8, two variable inequalities. The good news is you've probably seen this before, so a lot of this section is going to be just basically a repeat of things you've seen probably in Algebra 1. So if it looks familiar, don't be surprised. So here we go. First, kind of like a recall to kind of build connections to things that we've already talked about in recent days. A solution. That's a bigger word than you might realize, kind of in the grand scheme of mathematics. But anyway, a solution is what can be substituted into the equation or inequality to make it what? Sorry, excuse me. True. Excuse me. And another kind of recall bullet point here. A solution to a linear equation like this. This is an example of a linear equation. So let me kind of backtrack here, especially with that horrible coughing. So a solution is what can be substituted into the equation or inequality to make it true. Like it replaces the variable to make it true. But a solution to a linear equation, that's kind of like its own separate little recall, because it's kind of upping the ante with having not just one variable, but two variables, an x variable and a y variable. So for something to be a solution to this linear equation, it actually has to be a pair of numbers. You need like a couple of numbers together. One number that's plugging into the x, another number that's plugging into the y, to make this equation actually true, to actually make 2 times x plus y actually equal to 5. So here, one example of a solution might be, like if x were to equal 1, along with y being equal to 3, because then 2 times 1 plus 3 actually does equal 5. So 1, 3 would be an example of many solutions to this linear equation. Actually, how many solutions are there to 2x plus y equals 5? That's right. There is an infinite number of solutions. There's literally an infinite number of pairs that could make 2x plus y actually equal 5. So that's kind of stuff that hopefully, at least with what we've been doing in recent days, or from your more distant Algebra 1 past, that should make a lot of sense to you. Now here's a little kind of activity. Again, don't write any of this down yet. So here's the activity. Is any xy pair that solves this linear equation, equal sign, so equation, is any pair that solves this equation also a solution to this linear inequality? It's got the greater than or equal to symbol, so it's now officially an inequality, not an equation. And obviously you've probably noticed that literally the only thing different from this equation and this inequality is the symbol. This equal sign is now a greater than or equal to. So, for example, what do you think the answer is, first of all? Do you think any pair that solves this also solves that? maybe a little bit of help, like let's say a pair that would solve the equation might be, let's say if you plugged in 1 for x, that would make y equal what? 3 times 1 is 3, minus 4, that would be negative 1. So maybe just make that a little bit smaller. So this would be an example of an xy pair that solves this equation. Would this ordered pair also solve this? So if you plugged in negative 1 in for y and 1 in for x, would it make a true statement? Like, is negative 1 greater than or equal to 3 times 1 minus 4? And again, I can't remember if I actually said this and let the cat out of the bag, but the answer is yes. Okay? The answer to this first question is a big time yes, because of the equal, like y could be greater than or equal to 3x minus 4. Here, this is just literally just y is equal to. So this covers all of this. Okay? If they are, graph them below. So we got like 1 comma negative 1, which is right there. Okay, what are a few more? Okay, like let's say if you plugged in, how about like negative 1? Okay, what about like negative 1? If you plugged in negative 1, so I'm talking like a solution would be negative 1 comma what? If you plugged in negative 1 for x, that would make y negative 7. So negative 1 comma negative 7, which is a little bit tough to graph here. Not super weird. I mean, maybe we can just kind of like forget about this one. But, yeah, whatever. Negative 1, and then that'd be negative 5. So, like, we'd have another dot down here. So it's up to you if you want to actually draw that dot. But, so another one, how about like 0? Like, what if you let x equal 0? 0 comma what would be a solution? 3 times 0 is 0, of course. And then minus 4 would be negative 4. So 0 comma negative 4 would be a solution. And feel free to write some of these down, you know what I mean? 0 comma negative 4, feel free to write these down. How about if you plugged in 2? Let's just do like one more, Another solution would be 2 comma what? 3 times 2 is 6. Minus 4 is 2. So 2 comma 2 is right there. 2 comma 2. And, remember we said that there is technically like infinitely many of these, right? Like I said, we could have a dot down here. This creates a line that goes on, forever. So, oh boy. So there's that line. We graphed 3 of the points, but this line contains billions and billions and billions and like really infinitely many dots. There's dots everywhere. Because again, like just to remind you, there's a solution here for like x equals 1.5. Like if we plugged in 1.5, 3 times 1.5 should be 4.5. And then 4.5 minus 4 is 4. So we have a solution that says 1.5 comma 0.5. So there's a dot right there. So there's dots everywhere on this line, and it keeps going forever in both directions. So then we move on to question 3. If there are any other solutions to the entire inequality that you can think of, graph those dots. Okay, so all the points on the line solves the just having y being equal to 3x minus 4. But when you include the fact that y can also be greater than 3 times x minus 4, that opens up the door for more solutions, right? Like if you plugged in 1, 3 times 1 is 3 minus... But, wouldn't negative 1 comma, 4 be a solution as well? Because isn't 4 bigger than or equal to 3 times negative 1 minus 4? Heck yeah, so negative 1 comma 4 is a solution, right? How about like, what if you plugged in negative 2 for x and 5 for y? Would that make a true statement? 5 is 5 greater than or equal to 3 times negative 2 minus 4. 3 times negative 2 minus 4 is like negative 10. There's a lot of numbers that are larger than negative 10, including 5. So x is negative 2, y is 5. That's included, right? Isn't that included? How about like, how about negative 3 in for x? How about negative 3 for x and negative 1 in for y? Does that make it true? Is negative 1 greater than or equal to 3 times negative 3 minus 4? 3 times negative 3 minus 4 gets you like negative 13. So yeah, negative 1 in for y is bigger than that, and that makes it true. So negative 3, so there's another dot. And maybe you're starting to see by now that there's going to be, man, like a whole new world of solutions, okay? In fact, and again, you might already know this from your distant past, but there's actually solutions literally everywhere on this side of the line. Like there's literally, I could put anywhere, just say stop and boom, right there. I don't know what those points are, or what those coordinates, but I know it's going to be solving and making this true. Blah, 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 boom, right there. I mean, I don't know what those numbers are. It looks like something like negative 2 point something, comma negative 2 point something, but that's a solution, or negative 5, comma negative 2. Again, there's literally solutions everywhere. So here, number 4, how can we represent all the solutions? Oops. You can write down here something like by shading on one side of the line. Okay? So we can represent, because we can't put like a bajillion dots here. So what you can do is just kind of shade everywhere, because you're literally like coloring in all the solutions. Okay? And remember, there's solutions on that dark purple line, and then in this like lighter purple shading, there's just more and more and more solutions. There's literally solutions everywhere. All right? So if I just were to show you this graph, and I said this graph is the graph of this linear inequality, is 3 comma 5 is 3 comma 5 right there. Okay? Right here. Oh, geez. Is 3 comma 5 right here, is that a solution? You'd say yes, because it's on the line. And if I said, is 0 comma 0 a solution? You'd say yes, because it's in the shading. If I said, is 5 comma 0 a solution? You'd say no, because it's not in the shaded area. Now compare with this example where it says graph y is less than negative 2/3 x plus 4. And as we go into this graph, try to think about this. Do all the xy pairs that solves the equation of y equals negative 2/3 x plus 4, do all of those same xy pairs also solve this particular inequality? What do you think? Like a solution to this equation would be, let's say, like 3. If you plugged in 3 for x, I think y is going to equal 2, I believe. So 3 comma 2 solves this equation because 2 for y literally equals negative 2/3 times 3 plus 4. It's like it makes the whole thing actually equal. But if you plugged in the solution of 3 comma 2 here, you would have it say 2 is less than negative 2/3 times 3 plus 4. Okay, that's not equal. That's like saying, we might as well write this out. Oops-a-daisy. Oh, for goodness sake, man. That would end up getting you, oh boy, let's start over again. So let's say, this is where I wish I was just at my active board. So let's say 2, oops, sorry, it was 3 comma 2. All right, so 3 comma 2, if you plugged it into here, you would end up eventually, obviously there would be a 2 right here, right? If you plugged in 2 for y, you would obviously have a 2 over there. On the right side, you would end up doing like negative 2/3 times 3, and that would get you negative 2. And then when you added the 4, you would end up with 2. So, is 2 less than 2? And the answer is no. Okay, it's not. So you can kind of see, since this is strictly less than, any xy pair that solves this does not actually solve this inequality because it's just less than and not less than or equal to. And so when we go to like make this graph, like we want to graph this line, but we got to remember that every ordered pair on this line is actually not a solution, like 3 comma 2. It's not actually a solution. So in order to represent that, and again, let's just, let's graph this line, right? Remember, y equals mx plus b. So my b is 4. That's my y-intercept. And then my slope is negative 2/3. That's a rise of negative 2 and a run of positive 3. So, I mean, I guess I'll just kind of plot those 2 dots there. So that's where my line is going to be. But as I was saying, in order to represent how I do have to draw this line, but every point on the line is not actually a solution, you make it a dashed line. Kind of like it's a ghost line. Like the line is there, but it's not really there. It's not actually a part of the graph of all the solutions. Okay, it's a dashed line, it's a broken line, it's like a ghost line. Okay, so there we go. So step number 1, graph the line or plane divider. Determine whether it needs to be a solid line or a dashed line. And this is where you should kind of write in, right here, that it's got to be a dashed line. Like, for example, write how, come on, man. Or, bam. So a dashed line would be a less than or a greater than. A solid line would be, why don't I just do this? I'll just do, good grief. So less than or equal to, greater than or equal to. So it's these two symbols that would have you doing a solid line in your graph, and it's these two symbols that would have you doing a dashed line. And then here's where step 2 gets a little more open-ended, okay, for us. Pick a test point, okay? Because here's the bottom line. You're going to be shading on one side or the other. You're going to be shading on one side or the other. Either all of the solutions live over here, or all of the solutions, all the solutions. I was going to say all the other solutions, but remember, we haven't even graphed any solutions yet because the line contains no solutions. So either all the solutions live over here, or all of the solutions live over here. And you can pick like a test point. And the classic test point that you would always probably want to pick, if you can, is 0, 0, Like, unless your line literally passes right through 0, 0, okay, in that case you couldn't use 0, 0 as a test point because you want to pick a point that's actually on one side. But otherwise, you should pick 0, 0 because it's the easiest point to plug in the numbers and check really quick. So you could just like pick like 0, 0, like plug 0, 0 in for x and y and actually see if it makes it a true statement. And if it does make it a true statement, bingo, that's where all your solutions live. But if it doesn't make it true, then it must be the other side that have all the solutions. But here's what else you can do. Okay? Here's a quicker shortcut rule of thumb. Ready? And you might want to write this down in your own words. So, as long as the inequality is in mx plus b form, which it pretty much will be, like why would it not already be in mx plus b form? You pretty much are going to have it b in y equals mx plus b form, or just mx plus b form, because remember you have to graph the line first. So if it's not already in mx plus b form, in order to graph your line, you're going to put it in mx plus b form. So when I say, to use this rule of thumb, it's got to be in mx plus b form. That's almost like a moot point because it's probably almost definitely going to already be in mx plus b form. But again, as long as it is in mx plus b form, just look at the symbol. And if it's, and this is where you got to write this down carefully, if it's a less than or equal to, anything involving less than, you're going to shade below. You're going to shade below the line. And if it happens to be a greater than or equal to symbol, you're going to shade above. Which makes perfect sense. So this is a less than, so you're going to shade below the line. Okay? And so here's what this means. This means like if I would have went the testing a point route, like testing 0, 0, 0, 0 is right there. So I gotta assume that 0, 0 would plug into here and prove to be a solution. Like if you plugged in 0 for y and 0 for x, let's say, is 0 less than negative 2/3 times 0 plus 4? Yeah, because over here would ultimately just be 4, and 0 is less than 4. So that right there is in fact a solution. Because it lives in the shading, So, but again, to kind of repeat and summarize, you can do a test point, 0, 0 if possible, would be easiest, or you could just go with the shortcut of less than or equal to, you would shade below, greater than or equal to, you would shade above. And if you happen to be in a situation where they showed you a graph like this, Let's say you had no idea what the inequality even was. Like all you had was the graph to look at. And they said, so tell me, is 0, comma 4 right there, is 0, comma 4 a solution? You would say what? You would say no, because it's a point on a dashed line. Any point on the dashed line is not actually a solution. If you said, what about 3, comma 4, right there, is 3, comma 4 a solution? You would say no, it's not. It's not in the shading. It's out here in the non-shaded area. But if they asked you about points like 0, 0, or 1, comma 2, or negative 3, comma negative 3, all of those ordered pairs would be solutions because they live in the shading. All right. So, and then here's this example. Just a different example. So let's do one kind of start to finish without any kind of blips or losing momentum, okay? So here, 5x plus 3y is less than or equal to 9. The first thing you realize is that we have to graph the line, but I can't graph the line until I solve this for y. Right? So first I got to get this into mx plus b form. I'm going to start doing that by subtracting the 5x away from the left side over to the right side. All right, so that's going to leave 3y by itself. And then over here, hold on. So what's the right side become? Remember, 9 minus 5x, those don't actually combine together. They're not like terms. So these are going to remain separate terms. And as I may have said already in class, you can write it as 9 minus 5x. But since we literally want it to be in mx plus b order, you probably want to put the minus 5x. This is messing with my OCD now. I think I remember what, yeah, buddy. And it's not even bold. And then the plus 9. Okay? So that's what we have right there. And then we would divide both sides by, and I'm just going to tap out here and start using my mouse pen. So we would then be, I hope it's not way too sloppy. Oh, God. We would divide both sides by 3 and end up with y by itself. And then we have less than or equal to. And so we got to divide both of these terms by 3. This is so ugly. Negative 5 divided by 3 is not clean. And it can't really even be reduced, so it just stays negative 5/3 x, which is fine because this is going to be the slope, and slope is good as a fraction, right? Yeah. And then 9 divided by 3 is 3. So now we can plot our line, now that we know our b value is 3 and our slope is down 5 over 3. Okay? And now you got to remember how the line you draw is either solid or dashed based on the symbol. And so based on our less than or equal to symbol, that means it's going to be a solid line. Okay? Solid line. And as far as the shading goes, it looks like 0, 0 is open to be tested, but we can just go with the fact that it was a less than. It's a less than or equal to, and if it's a less than, that means we're going to shade below the line. So 0, 0, it looks like, is in fact a solution, and it would have worked out. But so there's the shading below. Okay? And then we just throw a big old wrench into everything, and we actually throw this little plot twist in. Graphing two variable absolute value inequalities. Holy crap. So, I mean, we can actually remember and kind of compare back to how when we were doing absolute value, just like equations that were functions, it would make a v, you know. Well, now we have an inequality kind of combined with that, and so it's still going to be a v graph. It's still going to be a v graph, but since it's going to be now an inequality, that just means, like you might expect, actually, that the v now could be solid or dashed, depending on the symbol. Same reasoning, same you base your decisions based on the same thing. But the v could be solid or dashed, and there's also going to be shading. Okay? So the extra curveball here is that before we can properly graph this v, we have to get y by itself. Okay, so that's a little bit of an inconvenience, and but whatever. The first thing you would do is subtract 3 to the other side. Okay, and that gets us to here. But is y by itself yet? Because again, we're not really going to be able to graph our v that easily unless y is all by itself. And as you can see here, this says negative y. So we have to kind of undo the fact that it's a negative. We just want it to be y. So we're going to do what to both sides? We're going to divide both sides by -1. Okay? How do we do that? Over here, that's just going to make it y. Like over here, you're just doing what you got to do to get y by itself. Over here, you're going to have to divide this whole chunk as like a term. So divide this part as a whole by -1, as well as this -3 term is also going to get divided by -1. Not to mention what else? Do you remember what happens when you divide both sides of an inequality by anything negative? What happens? You have to reverse the inequality symbol. So don't forget that. Because again, at the end of the day, it's an inequality and all the rules still apply. Dividing both sides by anything negative flips this to a less than. So this would just have a negative out in front now. So dividing this whole thing by a -1 just sticks a negative out in front of the whole thing. And this -3 becomes a +3. So now we're actually finally in a position to graph this v, to graph the v. And then I might as well say it now. When we go ahead and graph this v, is it going to be a dashed v or a solid v? The fact that it's a less than makes it what? Makes it dashed. It's going to be a dashed v. Don't forget that. Don't lose concentration. Now, the v, let's see here. This +1 would take the original parent graph and move it to the where? This +1 would shift your parent graph to the left 1, and this +3 would shift it where? Up 3. How about this negative out in front? What does that do? Remember, this number out here would be like the slope or slopes of your v. But the fact that this is negative means your v is going to what? Be upside down. So this whole time we were using the family concept where we were comparing this to the original old, see it's right here in green, we were comparing this to just y equals the absolute value of x. So like I just said, so this graph is going to be this graph but shifted up 3, left 1, and flipped upside down. And we're not really going to have to change the slopes technically. That's going to be the v. And it's going to be dashed, and there's going to be shading. And since it's a less than, we're going to shade below the v. So your final graph is going to look like this. The vertex goes here because we shifted left 1, up 3. That negative turns it upside down. It's just going down 1 over 1, down 1 over 1, down 1 over 1, okay? It's dashed, all right? And we're also shading below. So that's the final graph of, what was originally this absolute value inequality, but it's probably better written, way better written, like this, where y is all by itself. Okay? Hopefully that makes sense. Obviously, in person, we can do more examples. We can go over, plenty more homework problems. Feel free to ask questions next time you see me, or shoot me an email and we can do more examples together or something. But one more example here in this video, and here we go. This is another plot twist, okay? And I don't even really know for sure, especially if you are absent and have been absent. You might have never seen me, even if you've been in class, we might have not done an example like this, This is actually not what I would call vertex form. You know why? Why would I look at this over here as an absolute value inequality or whatever? Absolute value of 2x plus 6 plus 3. Why would I not look at this and go, oh, this is in vertex form, and I can just do all the family stuff, the shifting, maybe the flipping, the stretching, the whatever. This is not what I would call vertex form because of the what? Because of the 2 right there. Let me, it's already right there, I think. This is what we wrote down, perhaps, in the last section, okay? See, we knew what to do when there was like a random number way out here. We didn't have a number that could have been right in front of the x. In here, it's just x. But if we all of a sudden put a number right there with the x, that can change things. And like just to be safe, I'm going to show you like a whole different method to get the job done here. Because I would not necessarily just go, just go left 6 and up 3 and blah, blah, blah. Let me show you a whole new method, okay? We're going to call this the 2 lines method. The 2 lines method. So we're going to graph 2 lines. They're going to cross somewhere. And I want you to remember that ultimately, right? Ultimately, the graph of an absolute value equation or inequality is a v, So we're going to have 2 lines that just cross, and they're going to make an x at first. 2 lines that cross make an x, and we're just going to go with either like the top half of that x, which is a v, or the bottom half of that x, which is a v. It's upside down v, but it's a v. And whether we go with like the top half of the x or the bottom half of the x is just going to depend on, is there a negative number way out in front here or a positive number way out in front. Okay, so here's how we do the 2 lines, which, by the way, less than or equal to is our final v going to be a solid v or a dashed v. It's less than or equal to. So it's going to be a solid v. So we're going to draw these lines and make an x, and we're going to do it very, very lightly, because remember, at the end of the day, we're not going to keep the entire x. We're only going to end up keeping the top half or the bottom half. So that's why I'm using like a lighter blue here and like a pink, because you want to draw the x pretty lightly, you know. So here's what we do. We take absolute value, and we're going to make two cases, because absolute value pretty much works very, very nice with having two cases, okay? The positive case and the negative case. So literally, that's what we're going to do. We're going to write two equations. One where we're going to go with like the positive quantity of 2x plus 6, see? Like just 2x plus 6 as a quantity, positive. And then the other situation is like the negative entire quantity. See, negative outside of like the whole bubble of 2x plus 6. So those are my two cases, right? And again, it's always going to be plus 3, because we're only doing a positive and negative version of this absolute value chunk. All right? So this is what's going to create our two different lines. And if you take this all the way to the end, you can just drop the parentheses because there's nothing out here worth distributing. And you end up with y equals 2x plus 9. So that's going to be a simple matter of, so there's the y-intercept, and my slope is 2, aka 2 over 1. So that would be like up to, I'm out of bounds. So let's just go in the reverse direction. So it'd be there. And, maybe there, and then maybe, there, and then maybe there, okay? So this line is going to have a slope of 2 and a y-intercept of 9er. And again, very lightly, right? Very lightly, okay? There's my first line from like my quote-unquote positive case. My negative case, first you're going to have to distribute the negative. And that makes it negative 2x minus 6 with the plus 3. And ultimately we end up with negative 2x minus 3. And now that we know that b is negative 3, and that my slope is negative 2, or negative 2 over 1, that means down 2, right 1. And we have one dot left over to go in the reverse direction. Why not? And so, kind of wanted that to be pink, I guess, which I can make that change. No big whoop. I said, yep, there it is. There's pink. Yeah. Okay, sorry, I'm like OCD-ish. So there again, so I hope everyone's with me so far, okay? We're going with like the two lines method to make an x, which is ultimately going to be just a v, because we did like the positive 2x plus 6 case and the negative 2x plus 6 case, where we had to like distribute the whole negative. Now, because our I guess we can just still call it like an a value. The a value out here is positive. It's positive 1. That means our final, v graph is going to be right side up. So we're going to go with like the top half. Okay, we're going to go with the top half of the v. So now we're going to get way darker here. Yes, okay. I forgot to make it bolder. But, so now you can kind of like disregard this part of it, because you can just like kind of erase it, because we made our x so that we could properly get, the v, okay? And now, and again, just a reminder, it was supposed to be a solid v. It could have been a dashed v, but because it's less than or equal to, it ended up being a solid v. And remember, what else do we need with an inequality? What else is going to be a mandatory, inevitable part of the graph? We also need what? We also need shading. It's going to be either shading above or below. Above the v or below the v. That was an accident. But as it turns out, it is a less than or equal to. So we are going to be shading below. As nice and as neat as possible. So shading below the v. Because again, it's not an absolute value equation. It's an absolute value inequality. Which means the v could have been dashed in the right circumstances. And there's going to be shading either above or below. And I hope this new two lines method made sense, because you might have to bust it out every now and then if there's like a number right there in front of the x inside the absolute value. But that should do it for section 2-8. A lot of it was stuff you've seen in the past, graphing these linear inequalities. But we kind of took it to the next level when we threw absolute value with it in there. But yeah, that's it.